Maryland Metro News Network. Today's program begins our two-part series on the generator circuit. This system provides the majority of the electrical power used by the aircraft systems. Now, if you have any questions or confusion regarding what has been covered in the DC power and distribution tapes, we hope you have done some supplemental study or asked someone for some individual help. While the generator system is not in itself really more difficult or theoretical than the feeder fault system, it is more complex. Now let's roll the program.
The DC generation system can normally provide as much as 300 amps of direct current from each generator for use by electrical systems on board the aircraft. To produce, control, and direct this current is a formidable task. Before we begin, let's discuss some electrical generation systems basics. During our discussion of the feeder fault system, we mentioned the term induction. We saw induction at work in solenoid valves and coils of wire. Generators use induction to produce electricity. We know that passing a current through a coil of wire will produce magnetism. This invisible magnetic field can be used to do simple work, such as actuating a relay, opening a valve, and so on. Let's now discuss this magnetic force in more detail. Let's set up a typical demonstration circuit. We'll start with a conductor wrapped around an iron bar or core. We'll use a small power source to provide current flow through the inductor. A magnetic field is a primary product that results. This magnetic force can now be used to yield a secondary product, work. In the case of a relay, the magnetic force is what moves the contacts. By changing the number of conductors or the strength of the current, the magnetic field output will be directly affected. Of course, the amount of work the device can do will be affected as well. In this example, we're using electricity to produce a magnetic field, which then performs mechanical work. This process can be reversed. We can use mechanical energy to produce electrical current flow. Let's see how that process can be reversed to produce electricity, using this simple example. Between the two legs of this horseshoe magnet is an invisible magnetic field. This invisible concentration of magnetic field is called flux. Suppose we consider these lines of force and how we can use them to create electricity. Let's add another component so that we can begin to use this potential energy. This conductor loop, when rotated by some mechanical means, will cut through these flux concentrations. Each time it cuts through this flux, a small induced electrical voltage will be generated in the conductor. The lines of flux that flow across the magnet project in the same direction. Unfortunately, because our conductor is rotating, it is cutting these lines in two different directions on each rotation. The result is that each time the conductor cuts the lines, a small voltage is inducted. This voltage is alternating in direction because of the change in direction of the conductor relative to the lines of flux. This type of voltage is extracted from a device called an alternator, just like the one in your car. But our discussion today is about DC generation, and as such, the voltage a device like this would produce is of little use. A device called a commutator is attached to the conductor ends. This device allows us to extract electricity while the voltage being produced is moving in the correct direction. Now we have a device that, if driven mechanically, would produce electricity. But there are several problems shown here that make a device this simple impractical. First, using a permanent magnet to produce our field of magnetic flux is not workable. The weight would be enormous, and there is no way to vary the amount of flux that is produced by the magnet. Our conductor will only produce any electrical current once in an entire revolution. And we have no way to control the output of our simple generator, other than by how fast we rotate the conductor, or armature. Let's look at an actual generator to see how these limitations are overcome. We'll use this smaller automotive type generator. The theory and design of this type generator is similar to that used in the aircraft. Here's our armature. Note that there are many conductor wires, and our commutator has many more segments. Each of these segments is attached to a group of wires that essentially comprise one loop. Inside of the generator housing, we find no evidence of a horseshoe magnet. Instead, loops of wire are wound around forms to produce an electromagnet. Remember, the amount of magnetic flux an electromagnet will produce is dependent upon the amount of electric current we flow through it. By using this type of design, we can vary the strength of the magnetic field by varying the amount of current flowing through these windings. Not surprisingly, they are referred to as field windings. At the rear of the generator are multiple brushes. These are conductive devices that contact the segments of the commutator. They are carefully positioned so as to only make contact with the commutator segments that are producing electrical current flowing in the desired direction. Hence the term direct current, DC, or single direction current. The armature of the generator is supported on bearings at either end to allow it to be rotated. As the armature rotates, a small amount of electricity is being produced in each pair of windings and is transmitted through the brushes. By using many segments in the commutator, multiple brushes, multiple conductors, and multiple field windings, the output voltage is smooth and efficient because there are always two segments in contact with the brushes at a given point in the generator's rotation. The output of the generator can be varied by changing how fast we rotate it, or by changing the strength of the magnetic field produced by the field windings. The rotation speed is tied to the speed of the engine, and therefore is not practical to use as a means to control generator output. Varying the strength of the field is the most effective means to control the generator's output. This is accomplished by external circuitry that will vary the amount of electrical current flowing through the field. One of the generator system's primary responsibilities is to keep the batteries on board the aircraft charged during flight. Shown is a very simplified representation of the generator battery charging system. These simplified drawings are not meant to show exact positioning or the total circuit and components, but a workable means to easily explain the operation of the system. We're using one battery and one generator, although there are obviously two of them in each aircraft. The battery and the generator are both electrical sources, and both can supply current to electrical loads connected to the aircraft's bus system. In operation, the generator output is regulated to approximately 28.5 volts DC, while the battery has a stabilized output of approximately 24 to 25 volts. When both the generator and the battery are online, that is, the generator main contactor and the battery relay are closed, both will attempt to supply the bus. Because the generator voltage is higher than the battery voltage, the battery will become a consumer instead of a supplier. The amount of current flowing into the battery will be dependent upon the state of charge of the battery. If the battery has just been used to start an engine, it will likely be low on electrical potential. When the generator is first placed online, significant current will flow into the battery. In fact, immediately after engine start, the batteries are usually the major consumers of electrical power provided by the generators. As current flows into the battery, the power provided by this current is stored in the battery. As the battery approaches its full storage capacity, the stabilized voltage of the battery will increase. This reduces the difference between the battery voltage and the generator voltage, which will cause the current flowing into the battery to decrease. In actual application, the current flowing from the generator into the battery will never totally stop, but will become extremely small as the battery approaches full charge. This is, of course, only the briefest description, but it does cover enough of the basics to discuss certain aspects of the generator's operation. While we're discussing the inner workings of a generator, it is worth noting that even its function can be reversed. Any generator can also be used as a motor by simply applying electrical power to the unit. Of course, it would not be a very efficient motor. This is why the starter generator contains separate windings to be used during the start cycle to improve the efficiency of the unit when used as a motor. Since these windings do not play a major part in generating electrical power, we'll discuss them during the program on starting.
Before we continue with our discussion on the generator system, we should cover some terminology related to this system. We'll start with the starter generator itself. Obviously, the absolutely correct nomenclature for this item is starter generator. For simplicity's sake, we'll often refer to it as the generator or the starter, depending on the subject being discussed. In all cases, whether it's being called the generator or the starter generator, we're talking about the same unit. While we're discussing the starter generator, the subject of leads should be mentioned. Early generators were supplied with wires, or leads, that would be used to connect to the applicable external circuits. Some older single-engine aircraft still use generators that are supplied with leads. Because of this, aircraft terminology has always made use of the phrase A lead, B lead, C lead, and so on. Of course, since these leads are removable on most modern generators, you could really say A terminal, B terminal, and so on. Even though it's slightly outdated, we'll continue to refer to these connections as leads because that's what most mechanics call them anyway. This, by proper name, is the generator control panel. It's often referred to as the regulator or the voltage regulator. Throughout these programs, we'll refer to it as the control panel or generator control panel because it really performs many more functions than just voltage regulation. This is a very important relay, often called the generator relay. Again, by proper definition, it is the main contactor. The status of this relay, whether open or closed, absolutely determines whether or not the generator is connected to the aircraft's wiring. Because of this importance, we'll use the terminology main contactor through these programs. Most of the remaining terms and names used throughout the generator system are fairly standardized. Now let's return to our program.
Now that we've covered the fundamentals of how generators produce power, let's discuss some of the key terms and conditions of a generator system. The first is regulation. DC generators are used to produce electrical power. Their operation must be regulated to ensure that they produce the correct voltage and that the maximum and minimum output is within the limits of the generator and equipment it powers. DC generators, if unregulated, could produce more power than they are mechanically capable of withstanding. Damage to the generator and/or aircraft systems could result. The second is reverse current. The generator must always be a current supplying device, never a current consuming device. Remember, we can motorize a generator by supplying electric current to it, rather than extracting current. Under certain conditions, such as during engine shutdown, when the generator rotation begins to slow down and the output slowly decays, the generator could act as a load on the electrical system and begin consuming electricity. Should this occur, damage to the generator or the aircraft wiring could occur. The third is overvoltage protection. If the generator and its regulating system should begin to malfunction and allow the generator to produce too high a voltage, damage to electrical components or the generator system could occur. Fourth is feeder fault protection. The generator wiring, like the battery wiring, must be protected against shorting to the aircraft structure. Should a short occur, the fault system must immediately disconnect the generator from the aircraft wiring. Since there are two complete generator systems on board the aircraft, an additional consideration must be made: equal sharing of the electrical load by both generators. We refer to this as paralleling, making sure that each generator is doing its share of the electrical work, no more, no less. The last function is automatic line contactor control. This function acts as a single point disconnection for the generator and the aircraft's wiring. Working with the other circuits within the generator control unit, the automatic line contactor function will open the generator relay and disconnect the generator from the aircraft's wiring during any abnormal condition. This circuit will not allow the generator relay to close if any abnormality is sensed in the generator's output. Now let's discuss the Merlin and Metro generation system from a component standpoint. The generator system consists of two primary components, the starter generator and the generator control unit. The starter generator is a combination generator and motor. As a starter motor, it is used to rotate the engine for starting purposes, and as a generator to generate direct current after the engine is running. The brains of the generator circuit is the generator control unit. This small black box incorporates the functions of voltage regulation, circuit and airframe wiring protection, and other critical functions. The generator control unit also contains fault protection circuitry, nearly identical to that used in the battery fault system. There are two generator control units, one for each generator installed in the aircraft. These units must talk to each other in order to keep the output of each generator equal, or in parallel. The paralleling function is the only connection between the two totally independent generator systems. Several relays are used in the generator system. The largest of these is the generator relay itself, referred to as the main contactor. It is installed on the right-hand side of each nacelle. This is the primary means of connecting and disconnecting the generator to the aircraft wiring system. Control of this relay is shared. When the pilot moves the respective generator switch to the on position, he is signaling for the relay to close. But the generator control unit can either not allow the relay to close or open it at any time after it closes, if the control unit senses any abnormal function or condition. Because of the DC generation system's importance to the aircraft's safe operation, the condition of this system is carefully monitored. Primary cockpit indications include the voltmeter circuit, which allows the pilot to determine the voltage at each generator. In order for the reading to be accurate, the generator switch must be in the off position, so that the generator is not connected to the aircraft wiring and supplying a load. The generator ammeter is used to indicate the amount of electrical power or current flow the generator is actually supplying to the aircraft bus system. A generator disconnect light senses the position of the main contactor relay. When the relay is in the relaxed position, the annunciator panel generator fail light will illuminate. The generator fault circuit is almost identical in operation to the battery fault system. Although unlike the battery fault system, the two circuits are totally isolated and independent. The components of the fault system include transformers installed at each end of the major generator wires and the components of the fault circuitry itself, which is contained inside the control panel. This system functions exactly the same as the fault system discussed during the DC power distribution programs.
The next section will show the operation of the system in reference to pilot actions. This is an important point for mechanics to consider. Now, your perspective of the system and the pilot's perspective are often different. When he encounters a problem, he'll write that problem up from his perspective, how he thinks the system is supposed to work, and what he thinks it isn't doing properly. You will probably read this write-up sometime later, and often without access to the pilot to ask him questions. Countless hours are wasted every month because of misunderstanding between the pilot and the mechanic. Outside of the obvious things like trying to duplicate the problem before you begin working on it, the most important thing is to try and visualize what phase of flight the aircraft would have been in and what the pilot was doing when the malfunction occurred. And of course, the real bottom line is that if you are not sure what the actual squawk is, don't begin working on the aircraft until more information is available. Fixing electrical problems can be difficult enough. If you are not working on the right problem, your chances of success are entirely dependent on dumb luck. Now let's go back to our program.
Now let's discuss the overall operation of the system from a function standpoint. After the engines are operating, the pilot moves the respective generator switch to reset and then to on. The generator should be producing about 28.5 volts. The generator control panel will look at the generator's output and, if it is normal, allow the main contactor to close. The generator will now be connected to the aircraft bus. Because the bus system has many electrical consumers, or loads, that it is supplying, current produced by the generator will be supplied to the bus and then to the loads. The amount of current being supplied will be displayed on the respective ammeter. The pilot now moves the second generator switch to the reset, then to the on position. Its generator control panel looks at the generator's output, and if correct, closes the respective generator relay and places the second generator on the line. The generator control panels now must look at each other's output to determine if the generator they control is carrying its proper amount of load. The pilot now operates other electrical devices in the aircraft. These devices increase the load applied to the bus. Each generator control panel will signal its generator to supply more current to meet these new loads. If more current is extracted from the generator, there is a tendency for voltage supplied by the generator to decrease. This cannot be allowed to happen because most components on the aircraft require 28 volts to operate efficiently. Each regulator control panel senses that the generator output voltage is decreasing and immediately increases the strength of the field current. The reverse is also true. When loads are removed from the bus, the generator output voltage will tend to rise. The control panel senses this and decreases the amount of field current, thereby decreasing the generator's output to the correct value. This allows the generator to produce additional electrical power to supply the bus and still maintain the proper output voltage. As the control panel is increasing the field strength of its generator, it must also look at the output of the other generator to ensure that the sharing of the load between the two generators remains equal or paralleled. Now the pilot has completed his pre-flight activities and begins to taxi for takeoff. As he advances the speed levers, the engine RPM increases. Since the generators are now being rotated faster, they would produce more electrical power. Again, the generator control panel senses this condition and decreases the strength of the generator field to maintain the proper output voltage and load sharing. During flight, as the electrical loads are increased and decreased, the generator control panels must increase and decrease the output of each generator as well. If at any time either control panel senses that a fault has occurred in its generator wiring, it will immediately open the respective generator relay and disconnect the generator from the bus. The generator control unit for the opposite generator will sense this condition and increase the output of its generator to compensate. The generator control panel plays the major role in controlling the safe operation of the generator. Let's look at the circuitry and inputs that allow it to accomplish this feat. First, terminology. The generator control unit performs many functions besides regulation, but the unit is almost universally referred to as the voltage regulator. Most mechanics simply refer to this device as the voltage regulator or regulator. In actual fact, it performs many functions besides regulation. In order to determine what is happening in the generator circuit and what to do, the control panel must be able to sense certain key points in the system. These include generator output. This is sensed at a point before the main contactor. Thus, the control panel can see the output of the generator even without the generator being on the line. This is a critical source of information because it is the control panel which ultimately closes the generator control relay, only if it senses that the generator output is correct. The voltage present on the bus. While we say that the control panel is controlling the generator output voltage, what it's really trying to do is regulate the voltage on the DC bus system. It must obviously have a means to sense bus voltage. What the other generator is doing. A single wire from pin K of each regulator unit connects the two control panels together. This link allows both control panels to compare their respective generator's output and adjust it accordingly. The condition of the generator wiring. Because the control panel is also tasked with protecting the aircraft against a fault in the generator wiring, it must have a means to detect faults in this wiring. Transformers, identical to those used in the battery fault circuit, are employed. Circuitry within the control panel unit, nearly identical to that found in the feeder fault protection panel, is used to monitor and, if need be, disconnect the generator from the aircraft's wiring.
We hope you've enjoyed this look at the generator system. In part 2 of this program, we'll get into a much more detailed look at the internal operation of the control panel and the theory behind the operation of the overall system. Until then, good flying and good maintenance.